welcome Malachi Schram to come up to the computer. Malachi is the head of data science department at Thomas Jefferson National Accelerator Facility in Newport News, Virginia. That's Department of Energy. His current research focus is uncertainty quantification for deep learning and new techniques for design and control. So the floor is yours, Malachi.
Great, thank you very much.
And PDF. And then let's show.
Work?
Oh, there we go. Now it works.
Okay, now it works. All right, great. Well, thank you very much for the opportunity to present this. Unfortunately, after I thought about this slide deck, I realized that I should have probably done a much better job at convincing everybody that uncertainty-aware machine learning is critical. If you do not have uncertainties in your models, you really don't have any real confidence in what you're predicting. And so this talk is going to be largely a kind of a high-level overview of some of the techniques, definitely not fully inclusive, of how we could approach integrating uncertainty-aware machine learning. There's very specific topics in this area. So there's a lot of work that's going on right now. I'll just apply it to particle physics accelerators, and then you'll have some examples of why we believe it's really important and where it can be used. But nonetheless, it's really critical that you do have an understanding of the uncertainties that your model has. And this has largely been an overlooked problem. When you say cats and dogs, who cares if you get it wrong? But if you have something that's critical, like an accelerator, and I'm trying to control it, and my predictions for what I'm going to control is off the rails, and I don't even know it's off the rails, then I've got a real problem. So those are things that really must be part of our systems. And for most people that do scientific work, this has to be a priority. So a lot of this work is done in partnership with SNS and Oak Ridge. In fact, I have one of my colleagues here, Pradeep, who will be speaking later on. And we work very closely together on a couple of projects, and those projects do include this uncertainty-aware effort. Also worked for Fermi Lab, which is close to Chicago, FNAL, and University of California. So again, this is a kind of a snapshot of a lot of different things that, but there's a lot of work in this space. So to encourage you to explore it. So I'm just going to have kind of three main topics. The first one is, what are we talking about in uncertainty quantification in this particular talk? I would love to talk to anybody that wants to talk in more details. This is really a small sliver of all the possibilities. And then some of the applications, specifically in accelerated physics. So for us, in the programs that we're doing, we have kind of some problem definitions. What are the requirements that we have? So we're really focused on things that have like large features, okay? And we also care about large data sets. That's what DOE typically has. And then we also want to have these safety constraints. We want to have some sense of, of a guarantee. And then also, if I'm going to put this on a control system, I need it to actually be able to do it in near real time, and it needs to be done with a single inference query. So those are kind of things that we're thinking about in this particular application. Now, there's a lot more opportunities for a wealth of different problem spaces, but this is kind of for this talk, that's what we'll focus on. And one of the things we want to tackle in particular is what is called out of distribution uncertainties. Well, what does that mean? What I mean by that specifically is if I train a model with a data set, that's my in distribution training data set. Now, it's quite possible that a sensor goes wrong or something is bizarre, or my data has shifted in my system. And now what I'm using in terms of my inference is no longer what was in distribution. That subset is no longer overlapping. And now I need to quantify how much different is my data that I'm currently using for inference relative to what I used for training, right? And that is really important when you do control systems or anything that changes over time, okay? And again, I mentioned we have to do this as a single inference model estimation. I'm gonna skip this. I'm just going to give some really high level, some of the most common techniques. There's a lot more than this, but I'll start here. So we have a couple of, some techniques, a large group of techniques that we can use to kind of start the game of how do I actually make these estimations. And we could actually start making research projects that kind of evaluate them, play them off each other and so forth. Probably the most common one for approximating Bayesian neural network techniques is the MC dropout approach. What you're effectively doing there is if you look, and let's see this pointer, and I apologize for people on this side. So if you look at this particular diagram, what we're doing is we have these nodes, and what we're doing is we're going to randomly remove some of those nodes from the actual neural network. The process of doing that is typically originally done so that you could actually avoid overfitting in your training process. But it was realized that if you actually use that in the inference part of the process, you could now actually mimic some statistical uncertainties. And so that's a very common technique that is due. It's pretty easy to do, but the problem with that one is it requires you to do multiple inferences in your inferences to take an aggregate to determine the uncertainty. So it's not very efficient in terms of performing that immediately. So it's slow. And it has other caveats that I'll bring up in a second. Ensemble techniques is a common technique to try to understand the model uncertainty, right? You take a lot of different models, the initializations are different. And at that point, when you take the aggregate of these ensembles, you've accounted for the variability from the initialization of your model. So that's another way to determine another form of uncertainty. And then one that I actually personally really like and need to explore more is quantile regressions. And the reason why that's really interesting is because now you're going away from the idea of a Bayesian Gaussian assumption, and you actually have quantile, so you have asymmetrical uncertainties. That is a very nice feature when we're considering things that have boundary conditions. The challenge with that is it doesn't actually, in most of the implementations that are available online that you can find, will never have the proper boundary conditions implemented. So you can still go into an physical region of phase space in your prediction uncertainties. So the predictions will be fine, but the actual uncertainty will go into an unphysical area. And those are the same for all the other ones. But again, the quantile gives us this asymmetrical thing. That is actually something that we have. As much as everybody loves the central limit theorem, it doesn't apply for everything, right? And so these are the types of techniques that you could explore. And so here I'm just going to kind of give you an illustration of how they work and how they don't work. So in the top figure, what you're seeing here is in the first column, what you're seeing is just the predictions. So I have a blue class and an orange class, and then I have a third class, which is red, which I did not use for training. So I know nothing about that sample. So I trained my model on this blue and orange. I get some really nice separation, and I could do that for the top one is just a deterministic model. Awesome, I've got it right. The next one is just an MC dropout. You can see that now the predictions around the boundary conditions are a little bit smeared, what you would expect. And then also an ensemble technique, you get a little bit of smearing. What I want to bring your attention to, though, is on the next column, those are the uncertainties of those predictions. And they're pretty well saying that I'm pretty bloody sure I know what I'm talking about. But now if I introduce that red dot, guess what? I'm obviously going to get that one wrong in this problem. So anybody that's using classification that didn't use that red dot in their training sample would say, no, that's orange. Clearly wrong, Okay, so that's hopefully now everybody really realize a simple example of why this is so important. Now, probably most people maybe in this audience understands Gaussian process regression techniques or classification techniques. And that's a perfect example of how that model gets it right. And so you can see on the bottom figure, the left side, that red dot is now, if you look at the prediction, it's kind of like, 50-50. And if you look at the uncertainty, which is the one to the right, it's yellow, which is the highest level of uncertainty. It's saying, hey, I'm going to give you a 50-50, and I'm really uncertain about this, which is exactly what you would want. So that if you're doing some investigation and you're analyzing something, you better be telling the person that's asking you the question, hey, I'm going to give you an answer, but it could be rubbish because I'm really not confident because I've never seen this. There's a problem with Gaussian process for those that have used it. They already know the problem, the scaling problem. And so there are techniques to kind of relax and relieve that problem. So Gaussian processes, what they're really fundamentally doing is they're doing a point-to-point comparison between your data points. So they're understanding how these data points are correlated to each other. And because you understand those correlations, when a new data point comes in, it says, hey, I don't fully understand that properly. The problem with Gaussian processes, if you go through the math, which I will not do, it scales to the order 3, n to the order 3 of the data set, okay, at the very least. And the problem with that is if you have small data sets, this technique is being used all the time. It's fantastic with a caveat. You need to know what kernel you should be using, which most people don't. The other thing is, the other challenge is, so A, you need to understand your kernel, and B, it doesn't scale well. The solution to that is that you have a technique called random Fourier features technique. So this is a really powerful technique that essentially takes that kernel that you're using, that is a point-to-point kernel, which is the size of your data set, and now you make an approximation to it. So you say, I can reduce my size, which is n, to a smaller size that is m. And if it's small enough, then it's actually very fast to learn. And in fact, there's a nice paper and theoretical explanation of how it scales with dimensionality, and it's exponential as one expects because this is a Gaussian process. So you can see in this illustration, the exact solution of the kernel is this diagonal. If I do now these random Fourier features and I go through the training process, I can see that as I increase my actual size of my matrix, my covariance, at about 1,000, even at 100 random Fourier features, I'm actually getting this right. And so now I've gone through maybe 1 million to 1 million, and sometimes for our problems, we have billions to billions of data points. I mean, billions of billions is never going to be tractable, but 100 by 100, yeah, that'll work. So again, application, again, there's some caveats to this technique. If you're doing non-stationary problems, it will not work. But if you're doing stationary problems, you're good to go. And you also have to appreciate that your kernel approximation is a very important component. That really dictates what your assumptions are in terms of the relationship between the data points. So now once you actually have a way to mitigate the risk of, or the computational problems of any kernel approach, so it's not limited to Gaussian process, any kernel approach will have that problem. You can now start thinking about, okay, well, how do I fold that into, get the features of a Gaussian process, but fold it into a deep learning architecture? And so the first thing is, and the reason why we do that is we have large dimension problems too. So we're not just data limited. The first problem, the RFF approximation, deals with how much data we have. But the next problem is how big are our data features? And so now we have to go and take deep neural networks and we say, okay, well, we'll take that input feature space and we'll reduce it to a latent space that is small enough, and we'll feed it to the Gaussian process approximation technique, okay? And that's how we go about it. It's pretty straightforward until it's not. So it's not. There's now a constraint. When you contract a feature space, like input feature space, and you contract it to a reduced dimensional representation, what can happen? Well, you could lose actually the salient features of importance can disappear. And also you have some boundary problems. So what you sure that the distance, the point to point distances in your input space still are similar to those that are in your latent space, right? Because that's what you're basing all your uncertainties on is, hey, I have this point and this point, they're related this way. And if I change my feature space and I contract it, and these things, they don't have the same relationship, then you've lost everything. So it's really critical that you have what's called a BI-LIPSCHITZ constraint that says my latent space, the difference in the latent space variables are of order, hopefully close to the latent space, the input space that you're dealing with, upper and lower boundaries, okay? So those are critical components that have to avoid, again, the lower bound avoids this feature collapse. You want to make sure the features of importance are still preserved. And the upper boundary is you have to be able to actually deal with feature similarities. So there are some techniques, I'll go really quickly through this one. There are some techniques that are really interesting. A really good paper that talked about how do we actually do this BI-LIPSCHITZ constraint normalization. And they approach it using a spectral normalization approach. This is essentially how you modify the weights in your neural networks such that you actually preserve that distance. And so TensorFlow and some other PyTorch will have that implemented. Odd thing is they have different implementations that actually are different. So be careful. So you might want to actually explore what the heck they're doing because it's not what you think, probably. So now I'm gonna, unless there's questions, I'll just jump into some examples. Okay, no questions? So I'm gonna kind of use an example of errant beam predictions. Errant beams are essentially if I have a problem with my beam, I want to predict that it's not going to have some kind of failure, right? And so what we do is we work with Oak Ridge and SNS, of course, And they have their facility, which is an accelerator that delivers 1.4 megawatts at 1 GeV pulsar. And so what we have is a big project that we've been working again with Pradeep and company. And so what we have is we have the accelerator, we have a lot of different types of sensors. We have some conditional like set points and so forth. Those are the important things. You have this process like your time series analysis. You do some data quality, feature engineering, etc. And then you start doing some model building, fold in some uncertainty, and then you have some prediction, and then you can make either some optimal changes in the system to prevent catastrophic failures, or you can actually make some more subtle decisions. So that's the project. We're looking at various components within that system of the accelerator system and try to find ways to improve the operations and improve the science. So more specifically, I'll go into a little bit of the weeds of this. Here we have pulses that are being generated by the Accelerator Complex. We have what are called these micropulses, which are these the upper right figure, and they're spaced 16 by 6 milliseconds. Okay, those are the macropulses. Within those macropulses, there's these mini pulses, a lot of little mini pulses. What you're looking at effectively is sometimes what happens if there's a failure, one of the pulse in the middle, let's just say, will give you this really weird result. And it's obviously because it failed. And then we kick it back up and they start again. The thing is, we don't really want to say, hey, we found that it failed, because guess what? They already know that. What they really want to know is how can we actually tell this ahead of time? So can we use a pulse before that to kind of see if there's information there that's suggestive that we're going to get a failure? And so that's the work that we're doing. We're looking at these mini pulses and we're looking at them in detail and understand, can we extract something from that before the fault has ever happened? And our timeline now is 16.6 milliseconds. Now, of course, we realize, and we don't have this in this particular slide deck, that we could probably go further in time to or other pulses and still see those effects that we've identified. So a traditional technique that probably most people are familiar with is autoencoders. So one way to do this is I have a bunch of normal situations, and because I have a lot of normal information, I could train an autoencoder, and then I could look at the reconstruction error and say, okay, now this doesn't look like my normal pulses, and it has a really high reconstructed error. I'm going to say that I have a pending fault. The challenge with that is that's unsupervised, and the performance is typically can be So another way is if you actually already have some anomalies, you could do what's called the Siamese model, which is really a contrastive method. What you're doing effectively is you're taking the pulse that you think is normal, and then you feed it into a ConvNet, and you pick the pulse that is kind of like either normal or abnormal, and you also feed it to the same ConvNet. They're sharing the weights. And then you take the difference of those encodings, and that will look at the difference between the two pulses, not what the class of the pulse is. We don't care about the class. We want to know that it's different than normal. So that is actually typically much more powerful than something like an autoencoder. And that's why we went ahead. We also have a good set of references that allow us to do this too. So as an example, this illustration that I've presented before, Siamese models actually deal with this very nicely. If I have blue and orange, again, if I had a classification problem, I would have got the red one wrong. But because I say, let's say blue is normal, if I use a Siamese model, that red is still going to be abnormal. It's going to say, I haven't seen this because it's not close to my blue. And so Siamese models also have this nice feature that is very similar to an outer distribution property. So just again, some data preparations, we take a bunch of normal references, we have a bunch of anomalies, we intermix them together, and then we train them. So what you have is a reference waveform, which is input layer, an acquired waveform that is coming in real time, and then you have the neural networks, some definition of distance, which is actually a whole topic on its own. And then after that, some dropout layers, output layers, and then you say how similar it is. If they're very similar, 0, right? You want it to be lambda. So if you Euclidean distance, 0 is an actual number, and your weights will go there anyways. And 1 is when they're maximally different. So some of the results from what we did with the accelerator group is that we applied this in the experiment. And what we see here, which is the figure at the bottom, is the classification output on the y-axis and the actual classification on the x-axis. So something you probably haven't seen very very many times. The nice thing about this is, again, I know from 0 is what I think is normal, and I see that there is some blue, which is normal, and some orange, which is what we use to train. Again, keeping the same colors from the previous example. Orange, and there's a cluster there. So because there's blue and orange in there, there's some intermixing. We're less confident that we've got that one right because there is intermixing. As I move out into the classification, I'm getting close to 1, which is the abnormals. And there isn't really any blues. My confidence gets much, much better. My uncertainties go down, which is what one would expect. So this is kind of suggested that we're able to identify, we're able to see how confident we are because there is intermixing, and we also are able to predict nicely the other ones. We introduced a different anomaly, which is surprisingly similar to the original anomaly, but a little different. And you can see that the uncertainties there have elevated because we aren't quite as confident as we would have been with the original trained sample. This particular result has outperformed other techniques by about a factor of 4 up to now, and we're still working on this quite a bit. So this is still work in progress, but the other reason why you want uncertainty is in the event that you do see this high uncertainty, let's imagine it goes really high, it says, hey, I have data points I've never seen before. Maybe I should record those and look at them more carefully. And that's another reason why we want to do this. So it's not just that we have this particular figure, it's also to be able to say, this is really different. Measure, capture it and study it, do the analytics on it. Okay, we've put this on a real life system. I think Pradeep will talk about this more, but the bottom line is we can run this in real time. What we have, because we have a Siamese model, we have multiple references here, and then we can make multiple predictions. And what you see is there were some changes in the accelerator configuration from 60 hertz to 1 hertz. Our model completely went nuts, which is what you would expect. Try to quickly go over surrogate model. So now I've talked more about a classification type problem. You could also, of course, do this in regression problems. I'll kind of explain the motivation here. So with accelerators, we're looking at artificial intelligence, machine learning to improve the controls and operations. So what you saw with the previous one is we're trying to identify pending faults to avoid damaging the system and also to minimize the amount of downtime. In contrast here, we're saying, well, what if we can actually improve the control system itself? Now, how would we go about this? The first thing is we want to be able to reduce the beam loss, and we also want to use machine learning to do this. And so in the interest of time, I will probably skip a little bit, but the bottom line here is you have a magnet that is curving the electrons or the protons or whatever charged particle you have. And in this context, we want to make sure that that current is well calibrated or steered in the right way. And there is this nominal width of how it's steered. We want to squeeze that down so we actually have more precision in that controlling system. So the idea, the workflow that we had is, while we have a lot of historical data sets in Fermi Lab, why don't we take that information, create a surrogate model? From that surrogate model, we can make an environment, an OpenAI and GEM environment, learn some reinforcement learning, and then create a policy, pop that onto the FPGA, then tune the reinforcement learning, and then finally do some calibration. So I'll just talk about some of this. So the thing that matters here is that we don't have a physics-based model. This is actually really, really critical to understand. Because we don't have that information, some of the limitations of a machine learning model needs to be addressed. But the goal of this particular surrogate model is to really be able to take this temporal information and kind of be able to do future predictions. So we're taking a physical asset, making it a digital asset, the typical digital twin. However, we're not talking back yet. So we don't have a fully realized digital twin, but we have a digital model. So again, physical surrogate models have a well-defined boundary conditions, right? That's the thing that defines it. If you have general relativity or Newtonian physics, you know exactly where those models will fail. And so you know you don't explore beyond those points. When you're doing a data-driven machine learning model, you actually don't know that boundary. You're just taking the data. And in the event that the data, and if you're using this model for exploration, for optimization, reinforcement learning, you could be exploring in spaces that the model's never seen before, right? Which is kind of silly. So that's another reason why 5 minutes will go fast. So this is really why this is important for also optimization, is that you want to have a digital representation of your physical asset, but it needs to have uncertainty in the event that you want to do optimization. because otherwise your optimization is meaningless. Some quick results, and in the interest of time, I will skip this, but there was 2 publications we did. One was we use LSTM with uncertainties. We use MC dropout, which was the initial uncertainties thing that we did, but we've progressed. And then here you can see that the figures here are just reinforcement of the figures. X-axis episodes, Y-axis your reward. Reward is always higher is better. Red is actually our RL system. Black is the original system. So we're seeing about a 2x improvement in our actual ability to do that control system. Then we did another paper, I'll give some references in the link, where we actually are now starting to ask the question, what are these techniques are really doing? How are they actually representing the uncertainties? How do they capture OOD, like outer distribution? How do they capture in distribution? How are we calibrating it? So the problem with, for example, MC dropout by default, unless you do a very specific loss function, you will never get the calibrated results you want. You have to do it after the fact. You could actually do that clearly in training process by actually making the MC dropout parameter itself a parameter to be learned. And then you do a log term of the uncertainties. But nonetheless, what you see here is that we've compared, deep kernel learning techniques based on MC dropout and then quantile techniques. And when it's in distribution, they're really good. So the outer parts of, you have the high oscillation and the low oscillations. The low oscillations are the parts that are actually in distribution. The high oscillations are out of distribution. And you can see at the bottom figure, the technique that we're talking about, which is the Deep Gaussian Process Approximation technique, gives you a much higher uncertainty there, which is kind of what we want, because we want to say, hey, we're not quite sure what's going on. We also, in the right figure, have gone through the exercise of saying, what if we actually manually change some of these variables intentionally outside of the training scope? So at this vertical line, you see that that's where we start kind of cranking a dial on one of the variables, and you can see the uncertainty start growing. You see, quantile technique is clearly not actually getting the outer distribution component right. MC dropout is reasonably good, and then our technique starts a little sooner. So the path forward for us is we're still working on some of these problems. One of the questions that you saw probably is when you go from a high dimensional problem to a latent space, and then you take a distance because you have to do your BI-LIPSCHITZ constraints and so forth. One of the challenges there is how do you actually make sure that large dimension is properly represented in the uncertainties? So there's different techniques about how you actually take a distance. Like, what does a distance mean with 1,000 variables? Because one variable could be really off and the rest are good, and then you don't really see a big distance. But there clearly is, because that one variable is. So you could use extreme value theory, etc. Again, there's approximation trade-offs that you have to consider if you want to put this online. So if I have to take this Gaussian approximation technique, the kernel reduced, how small can I go before I lose all my abilities to do uncertainty quantification? And if I want to fit that on a smartphone or somewhere else, that approximation matters. And there's a lot of things that we can talk about. And with that, thank you very much. Appreciate it, and happy to take any questions. If there's time.
There is time. We have time for maybe 1 or 2 questions.
Yeah, so going back to your Siamese model, you mentioned that you're using a CNN to do this make-up model, which implies that you're feeding it the kind of graphical images of your input packets. Why did you do that and not the raw data? Am I misunderstanding?
So we use a conv1d.
Okay.
So that treats it like, so that you can use temporal data with a conv1d.
Gotcha.
Yeah. Does that makes
Yes.
okay? Yeah. So yeah.
We do have time for 1 more question, maybe as Carl's coming up to get set with his slides.
Going back to the Siamese network, so that your first part of the presentation was about doing a Gaussian. The output of your Siamese network is maybe 128 dimensional vector. How did you get uncertainty on those? Right?
Oh,
so for the Siamese model, you compare distance to a normal to it. You run it through the network, you get a regular one, and the abnormal one. and the distance between those encoded vectors is large. But you were talking about uncertainty, so do you have another Gaussian process on
Yeah,
top of that?
Exactly, yeah, yeah, so we squeeze it, we do a sigmoid to get your 0, 1 for abnormal versus normal, and then you put the Gaussian process layer, the approximation layer, because you can't use a normal DP.
Right, so really your Siamese network is acting as an autoencoder in that case. It's just you're not having another network to decode the thing. You're
Well,
just
we
getting
actually
a
do-
classification out of decode.
Yeah, the newer version, actually, we have an autoencoder branch, so we have two outputs, the similarity and the autoencoder, so that we can validate that the latent space captures the nuances.
I see.
So we do, to your point, yeah, we actually have an embedded autoencoder Siamese model working now. Yeah.
Thank you.
Thanks so much, Malachi.